Hey guys, welcome to chapter 4. It's me again, my face, yeah. Today we're going to discuss about chapter 4, network access. Mm, Let's begin. Network access. To support our communication, the OSI model divides the functions of a data network into layers. Each layer works with the layers above and below to transmit. Uh, yeah, layers of the OSI model are so closely tied that according to the TCP/IP model, they are in essence one layer. Those two layers are the data link layer and the physical layer. On the sending devices, it is the role of the data link layer to prepare data for transmission and control how the data access the physical media. However, the physical layer controls the data. Data is transmitted onto the physical media by encoding the binary digits that represented data into signals. On the receiving end, the physical layer receives signals across the connecting data media. After coding the signals back into the data, the physical layer passes the frame to the data link layer for acceptance and processing. Uh, this chapter begins with the general functions of the physical layer and the standards and protocols that manage the transmission of data across local media. It also introduces the functions of data, link layer, and protocols associated with it. Layer standards. The protocols and operations of the upper OSI layers are performed in software designed by software engineers and computer scientists. The services and protocols in the TCP suites are defined by the Internet Engineering Task Force or the IETF. The physical layer consists of electronic circuitry, media, and connectors developed by engineers. Therefore, it is appropriate that the standards governing the hardware are defined by the relevant electrical and communications engineering organizations. There are many different internal and national organizations, regulatory government organizations, and private companies involved in establishing and maintaining physical layer standards. For instance, the physical layer hardware media encoding and signaling standards are by defined and governed by the International Organization for Standardization or ISO, uh, the Telecommunication Industry Association, Electronic Industries Association or TIA, EIA, International Telecommunications Union or ITU, American National Standards Institute or ANSI, Institute of Electrical and Electronics Engineers or IEEE. Another topic to discuss with is bandwidth. Bandwidth. Hmm. Different physical media support the transfer of bits at different rates. Data transfer is usually discussed in terms of bandwidth and throughput. Bandwidth is the capacity of a medium to carry data. Uh, Digital bandwidth measures the amount of data that can flow from one place to another in a given amount of time. Bandwidth is typically measured in kilobits per second or KBS, megabits per second, Mbps, or gigabits per second, Gbps. Bandwidth is something thought as of as a speed and bits travel. However, this is not accurate. For example, in both 10 Mbps and 100 Mbps Ethernet, the bits are sent at the speed of electricity. The difference is the number of bits that transmitted per second. A combination of factors determines the practical bandwidth of a network. The properties of the physical media and the technologies chosen for signaling and detecting network signals. Physical media properties, current technologies, and the laws of physics all play a role in determining the available bandwidth. Other is throughput. Throughput is a measure of the transfer of bits across the media over a given period of time. Due to a number of factors, throughput usually does not match the specified bandwidth in physical layer implementations. Many factors influence throughput, including the amount of traffic, the type of traffic, the latency created by the number of network devices encountered between source and destinations. Latency refers to the amount of time to include delays for data to travel from one given point to another. In a network with multiple segments, throughput cannot be faster than the slowest link in the path from source to destination. Even if all or most of the segments have a high bandwidth, it will only take one segment in the path um, will with low throughput to create a bottleneck to the throughput of the entire network. There are many online speed tests that can reveal the throughput of an internet connection. The figure provides sample results of the speed test, which unfortunately I don't have, so I'll tell it anyway. There is a third measurement to assess the transfer of usable data that is known as good put. Good put is the measure of usable data transferred over a given period of time. Good put is throughput minus traffic overhead for establishing sessions, acknowledgements, and encapsulation. Now, to the next topic is media access control methods. Some network topologies share a common medium with multiple nodes. These are called multi-access networks. Ethernet LANs, WLANs are examples of multi-access networks. At any one time, there may be able a number of devices attempting to send and receive data using the same network media. Some multi-access networks require the rules to govern how devices share the physical media. The two basic access control methods for shared media is contention-based access. All nodes in half duplex compete for the use of medium, but only one devices can send at a time. However, there is a process if more than one device transmit it at the same time. Ethernet LANs using hubs and WLANs are example of all these type access control. Next is controlled access. Each node has its own time to use medium. These deterministic types of networks are inefficient because a device must wait till its turn to access the medium. Legacy token ring LANs are an example of this type of access control. By default, uh, internet switches operate in full duplex mode. This allows the switch and full duplex connected devices and send and receive. So guys, I think that was it. As always, thank you for watching, and I hope you learn in this short summary video of mine. Thank you and goodbye.